Your eyes are a very complex combination of big, small, and ultra-small structures. It seems that with every passing year, the more scientists look into our own eyes, the more complex this amazing structure becomes. There are very large, relatively speaking, structures that help us see, like the lens, which helps to bend and focus light entering our eye. Then there is a thin layer all the way at the back of our eye called the retina, which has cells called rods and cones, which transmit information provided by light via electrical signals up to our brain. Our cones help us see in color and during the day, while the rod cells help us see at night. What's really amazing is that while these cells are really small, there are even smaller structures that are part of the cells that help us see. Without them, the rods and cones would be unable to do their job. The rods and cones located in the retina are highly specialized neurons that convert information provided by light into electrical signals that are conducted to our brain. We call these cells by a general term known as photoreceptors. They are essentially little nerves with specialized endings called receptors, which catch light particles called photons and convert the information these photons provide into electrical signals that our brain can interpret and process into a visual image we can understand. You'd think that microscopic photoreceptors, called rods and cones, are as small as we can get in the eye, but you'd be wrong. There are even smaller parts of our eye that allow for our rods and cones to function. One of these tiny little things is a light-sensitive protein responsible for color vision located in the cone cells of the eye's retina, which we call photopsin. If you recall, our cone cells are responsible for vision during the day and for our color vision. Therefore, it should make sense that photopsins located in cone cells are sensitive to light and help in our ability to see color. Not to be outdone, the rod cells located in your retina have a similar protein. If you recall, rod cells are responsible for night vision. They have a light-sensitive protein responsible for vision in low-light conditions called a rhodopsin. The interesting thing about rhodopsin is how it functions. There's a little experiment you can do yourself to prove that what I'm about to say isn't a lie. Stay in a very well-lit room for about a minute and just look around as you hum and haw. After a minute passes by, step into a very dark room, like a bathroom, or just turn off all the lights if it's dark outside. You'll notice that if you try to walk around right away, you're likely to bump into things. If, however, you were to stand there and allow your eyes adjust to the low light for several minutes, you'll be able to see much better than you did immediately after you turned off all of the lights. This is all because rhodopsin proteins are inactivated by light, and the photopsins in your cone cells need light to see. Therefore, once the lights are turned off, your cone cells are useless, and it will take several minutes for the rhodopsin in rod cells to fully regenerate and give you the ability to see in the dark with maximal effectiveness. It's important to realize where rhodopsins and photopsins fit in our ability to see. Essentially, what happens is that light particles called photons hit photopsin and rhodopsin proteins. You can think of these proteins as light sensors. If a particle of light hits either one of these sensors, they change the shape of their protein structure. This change in shape initiates the first step in transmitting light information into electrical signals that your brain can understand. Once the protein changes shape, the cones and rods are excited to produce an electrical signal called an action potential, which travels to a very important and large nerve which connects to the back of your eyeball. This nerve is called the optic nerve and is sometimes called cranial nerve number 2. The optic nerve transmits information received from the retina to the brain. Once the brain receives this information, it will begin to process it and piece everything together to form what you see in front of you. Let's review one more time how the information provided to our brain via light is transmitted by very special structures. As a photon of light, the information-giving particle of light reaches the retina located in the back of our eye. It will activate highly specialized neurons in the retina that convert information provided by light into electrical signals, which we call photoreceptors. These photoreceptors, called rods and cones, have special proteins embedded within them. The cones contain a light-sensitive protein responsible for color, which we call photopsin. The rods have a light-sensitive protein responsible for vision in low-light conditions, called a rhodopsin. Once the rhodopsin and photopsin sense incoming particles of light, they change shape. And this change in shape causes the rods and cones to transmit electrical impulses into the optic nerve, which then transmits information received from the retina to the brain. Our brain then collects all of this information and processes it in order to form a picture of what you see in front of you.